Okay, hi everyone. So today we'll be looking at kinematics. So kinematics in one dimension. So there's a few things that we are going to look at. So we'll look at examples. So remember last time we spoke about vectors and scalars, and we said we have something called a number, which is a mathematical object. Then we have a scalar, and we had a vector. Okay, so today we are studying examples of these. So we are studying, say for example, for a scalar we'll study something called distance, or at least introduce it, time, and then the equivalent for a vector. When we have distance, we have displacement for a vector. Okay, and then the equivalent, there's no equivalent for time, but we also have something called acceleration. Yeah, so velocity, which corresponds to speed when we go to scalars. So here we have speed, and there's many other examples. Maybe let's just mention them, but we're not going to study them in this section. So for scalars we also have mass, we have temperature, we have volume, we have area, of course, and so on. So anything that just has a number and a unit, so it doesn't have direction. And then over here we can speak about pressure difference. So pressure differences, actually no, so just scrape that. Yeah, so there are other examples of vectors. Okay, so let's stop there. So for today we are interested in studying distance, time, speed, displacement, acceleration, and velocity. Okay, so let's start with distance. So distance, there are different symbols that we use for distance. Yeah, so for example, when we speak of gravitational problems where a body is falling or is being thrown up, we normally speak of a height and we use h. So in this case we use height. Normally people will use h to represent this, whereas if you have, say for example, a car moving along a road or in the x direction, for this we normally have distance, which we use s. Sometimes people use d for this, and distance, d, or height, or s, or whatever symbol you use, is measured in meters. Okay, so the SI unit is meters, and we just write the symbol m, so that's the unit. And then the formula, well, before we speak of the formula, we also have time. So we also have time, and time is normally by a clock or an equivalent, and we measure time in seconds, so that's the SI unit. Sometimes it can be given in other units like minutes or hours, and you have to convert these into seconds if you are working with SI units or any problem that we have. So anytime we write down an equation, so say for example we write s is equals to vt, in these equations you always work with SI units. So make sure that you convert everything to SI units before you plug them in. Before you plug in the value. So for example, say a car is moving at 5 kilometers per hour, and okay, 5 is a bad number. Let's just change 5. Okay, let's choose a clever number. So let's say we have 3.6 kilometers per hour, and the car travels for say 2 seconds. Okay, and we want to know what distance it covers. You can see that here there's no match, so the time is in seconds and the speed or the velocity is given in kilometers per hour, so we need to convert the kilometers per hour to SI units, and we know that to go from kilometers per hour to meters per second, we just divide by divide by 3.6, then you will get that the car goes at 1 meter per second. And then it's very easy to find the distance S. Do not confuse also, most people would confuse these two. This S is a unit for time, it's in seconds, and this S is for distance. So it's one of the examples of scalars. They are not the same thing. So in this case, then we would get that S is equals to Vt, and V is just 1, and time is 2. So the car just covers 2 meters. Okay, in 1 second. And that's the distance that it covers. So be very careful with the units. So now we have spoken about time, and we just briefly spoke about distance. So now we are ready to, so let's just tick. We've spoken about distance, we've spoken about time. Now we are interested in speed. So let's look at speed. So what is speed by definition? So speed is the rate of change in distance. Okay, so how quickly we change our distance, and rate means per unit time. So then speed normally is given by a v. So then our v is equals to, it's the rate of change in distance. So that means I have distance over time. And normally people would then put some deltas to show that this is change. And the units for distance, if I can just remind you, was meters. The unit for time was second. So meters over second is just meters per second. Okay, so sometimes we use meters per second like that because that's just easy when you are typing. But both are the same thing. So that's our speed v. And the equivalent, so velocity, the vector equivalent of this, which is velocity, we just have the same equation, but now velocity v, and remember that for vectors we have a little arrow on top, so that is given by, now it's no longer the distance, so this s here was distance, now it's displacement, so it's the change in displacement over time. Okay, so what is the displacement? Displacement is just the distance with direction. Okay, so let's maybe look at 2 examples to try and understand what we are talking about. So say for example someone is running a 200-meter track. So remember that the stadiums for Olympics, for example, are in a circle like that. So from here to there is half a full round, so that is 200 meters. So someone runs from here all the way over there, then the distance they've covered, which I called S, so the distance S would be the 200 meter race, whereas the displacement, as you can see, is different. So displacement has direction is from the starting point to the end point, and you draw a straight line. So my line is not as straight as it should be, but it's one straight line and it's directed towards the finish point. So this is where they start the race, and that's where they finish the race. And you can see that the length of the track is not necessarily 200 meters, it's smaller than that, and it's almost like a football pitch size, so about 160 meters. Maybe let's say in the direction of motion, just for direction. So in the direction of motion, which in this case looks like east in my diagram. So we just say 160 meters east. So that's displacement. Okay, and we use a vector, so then we would write S is equals to 160 meters east. And also notice that sometimes, even though one has a non-zero distance, one can also at the same time have a zero displacement. So if we run the full 400 meters from here all the way around back to where we started, then the distance for that race is 400 meters, whereas the displacement is 0 because we are back where we started. Okay, so it's just 0. Okay, so if we can just go back, now we have covered displacement and we have covered velocity, and now we want to, and also speed, we want to look at acceleration. Okay, so what is acceleration? So let's just write it down first. So acceleration is the rate of change in velocity. It's also a vector, so it's not the rate of change of speed, it's the rate of change of velocity. So then of course you can guess the equation. We use A for acceleration, it's a vector, so I need the arrow. So A is equals to delta V, which is a vector, over delta T. And you can see V is measured in meters per second and T is in a second. So combining these two, the unit for acceleration is meters per second square, or sometimes it's written as meters times second to the minus 2. Okay, so that's acceleration. And yeah, so if I may just show you the plan for today. So we have discussed displacement, we have spoken about speed and velocity, we've just introduced acceleration. So now what we would like to do is to study equations of motion, or sometimes called equations of kinematics, for constant acceleration. Okay, so we want to study acceleration which is constant. So when A is constant, so constant means both direction and magnitude. So for example, if a planet is rotating around another one, so where you have the sun and say that's planet Earth going around the sun, if this is going around at constant speed, it's not going to give us constant velocity, because velocity is also direction. So when Earth is here, the direction is tangent. When the Earth is here, the direction is tangent. When the Earth is here, the direction is tangent. So you can see that there's a constant change in direction, so there is acceleration. And in fact, one gets centripetal or centrifugal acceleration, and that's just the gravitational force from Newton's law of universal gravitation. Okay, so there's a force of attraction that acts, and it's responsible for the acceleration, because remember that this is equals to mg. So there is gravitational acceleration over there. Okay, so we are looking at where both direction and magnitude are constant, and this is only possible when something is traveling in a straight line and at constant acceleration. Okay, so that's what we are interested in, and for this we get what are called the equations of motion. Okay, so there are 4 equations of motion. I'm actually going to state them and then define the symbols. So just a reminder, we spoke about speed and we said we use V for speed. We had S or H for distance, and we had A for acceleration, we had T for time. So using these symbols, we differentiate between speed. So normally we would have initial speed, so we use small letter I for that, just to say it's the initial speed. We also have the final speed or final velocity, and then when we speak about direction, motion in the y direction, we use h. In the x direction, we use s. So that's for y and that's for x. Okay, and then acceleration, there's a notation. So when we have free falling bodies or something going towards Earth, we normally use g for that, and g is known, it's 9.8 meters per square seconds. If you want to be more accurate, you can just say 9.81, and then t is always t. Okay, so depending if you can check, so here how many variables do we have? We've got 1, 2, 3, 4, because remember this is also a, and 5 with t. So with these 5, there are 4 equations of motion that help us to find any of the unknowns, and the equations of motion are the following. So we've got Vf equals Vi plus at, and remember that a can is substituted for g when we have a free falling body or any motion under the influence of gravity only. And then we have another one, which is Vf squared equals Vi squared plus 2as. And then we also have S or H is equals to 1/2 Vf plus Vi multiplied by T. So you can see, just to remind you, this is what we called the average velocity, VAV AVG. So it's just S is equals to Vt, which is the case where normally one doesn't have acceleration, but because the speed is changing, we have final, we have initial, there is acceleration here, which is constant. When there's no acceleration at all, Vi equals Vf, so Vi equals Vf if a equals to 0, and what we see is this equation just becomes S is equals to Vt, because you'll get V plus V, and that's 2V, it cancels the half, and you get S is equals to Vt. Okay, and then finally we have the equation of motion, which is S is equals to Vit plus 1/2 At squared. Okay, so if you check all of these equations, they only have 4 variables. So it's vi here, vf, a, and t. Here it's just okay. So here it's just vf, vi, a, and s. So here in the first equation of motion, we don't have s. In the second one, we don't have t. In the third one, I've already said we don't have a. In the final equation of motion, what we are missing is vf. So depending on what type of information you are looking for and what you are missing, you would then have to pick the appropriate equation of motion. Okay, so now we have also covered section 2.4 of the study guide, which is equations of kinematics or motion for constant acceleration. So all that is left now to do is to cover some applications and to do some questions. Okay, so just a reminder, in your book we are looking at sections 2.1 all the way up to 2.5. So 2.1, 2.2, 2.3, 2.4, and 2.5. Okay, so if there is 2.6 or anything else, that means it's not part of the syllabus, so we don't cover that. Okay, and so now what I would like to do, and a reminder also, this is on pages, so if you check your study guide, it's on page 40. We're looking at page 40, page 41, and page 42. So now we are going to go to page 42, and we are interested in looking at some examples. So let's look at example number 8 in the questions that we cover in lectures. So what do we have here? We've got a racer or a race driver that has made a pit stop to refuel. Okay, so the race driver has made a pit stop to refuel, and after refueling, so this is normally for your Formula 1 cars in a race, he leaves the pit area with an acceleration whose magnitude is 6 meters per second. After 4 seconds, he enters the main speedway. So yeah, this is a normal racetrack, and then at the same instant, another car on the speedway traveling with a constant speed of 70 meters per second overtakes and passes the entering car. And if the entering car maintains its acceleration, how much time is required for it to catch the other car? Okay, so I have already solved this problem, so my solution is over here, but let's just briefly discuss it. Okay, so what do we have? We need a new page, so let's open a new page. Okay, so we are looking at page, let me just double check, page 42, problem number 8. Okay, so let's relook at the problem. So we are told that we have a race car. So under the race car, so I'm going to separate the problem into two. I'll look at the race car before entering the pit. So this is before, entering the racetrack. So we are told that the driver makes a pit stop, so there's no information there, and then after refueling he leaves the pit area. So we know that the initial speed, which is vi, equals 0. Again, so before you even do anything with these equations, you need to choose the direction where you have positive. So I always choose positive to be the direction of motion. So direction of motion, because it simplifies the problem. You will get a lot of variables being positive and only a few being negative. So we know that the initial speed is 0, and then he leaves the pit area with an acceleration whose magnitude is 6. So acceleration in this case, because he's starting from 0, is accelerating the same direction. So a is equals to positive 6 meters per second square. If they said he is decelerating, then you would have a minus instead of a plus. or if it's accelerating and the car slows down, then you would have a minus. Okay, because that's opposing the motion. And then after 4 seconds, so it takes him 4 seconds to accelerate at that rate. He enters the main speedway. So here, this is before he enters the main speedway. Okay, so before main speedway, this is what we have. And we are told that, so let's say after over here. So now we have after. Okay, at the same instant, another car on the speedway traveling with a constant speed. So let's call this car A. After we have car B, and car B is traveling at V is equals to 70 meters per second, and it's constant. So that means the acceleration is 0, and we can just use S is equals to Vt. Okay, so what else are we told? It overtakes and passes the entering car. If the entering car maintains its acceleration, how much time is required to catch the other car? So this is important, and what we have is at some instant here, car A is accelerating at 6 meters per second, and we want to know what speed car A is moving at. So to find the final speed for car A, which I've called VA, we need to use equations of motion. So here we have VI, we have A, we have T. The equation of motion, which doesn't have S, so there's no S over here, is VF, equals VI plus AT. And we are looking at car A. So VF is just, our VI is 0, our A is 0.6, and our time is 4. So then we just get 24 meters per second. So we know that the speed at which the car A enters the main speedway or the main track is 24 meters per second. At the same time, another car B is moving at VB is equals to 70 meters per second. So this one overtakes that one, and later on they meet again, and this one, so car B is still moving at 70 meters per second. We want to know how much time is taken from when they pass each other to where they meet. We can see that both of these cars are going to travel the same distance S, and we start the clock when they meet, so they both have the same time, so which I'm gonna call T. Okay, so from car B, what we learn is S is equals to Vt, and V is 70, so the distance is just 70 times T. For car A, what we learn is we are looking for S also, so S is equals to VAT plus 1/2 AT squared. Just a small mistake there, so let's make sure that we erase that and get our pen back. So 1/2 AT squared, and remember that the driver A maintains the acceleration A, which is 6 meters per second squared throughout the race or before they catch up. So here we know that S is equals to VA is just 24, we don't know the time, plus 1/2, the acceleration is 6, we don't know the time, T squared. So combining these two, we get 24T plus 3T squared. But we said that the distance S is equal to the distance S for both A and B. So equating these two equations, we have 70T equals this number, which is 24T plus 3T squared. So 3T squared plus 24T equals 70T. And simplifying this, we get 3t. So 70 taken to the other side is negative, and 24 minus 70 is 46. So let's just see, 2050, yes, 46. So minus 46, t equals to 0. There's a square here, so taking out a common factor of 3t, I'm left with t minus 46 over 3 equals 0. So then we get our final solutions. So there's two solutions. There's t equals to 0 or t equals 46 over 3 seconds. Okay, so which answer is the correct one? We're looking at when they catch up. This is when overtaking takes place. So at t is equals to 0, that's where car A is overtaken by car B. So that's not our solution. And our solution for catching up then would be after 46 over 3 seconds. Okay, so it's about 15.33. So t is equals to 15.33 seconds. Okay, what was the question? So the question is, how much time is required for it to catch the other car? And that's the 43.33. Okay, so now we have looked at number 8. Now we are interested in number 7. Okay, so number 7.